Now let's turn our attention here to example number 3. This is going to be a problem that's very, very similar to what we did in example number 2. We're going to be asked here at the start to consider the parabola x equals y squared minus 1. Okay, now first off, this is an immediately kind of awkward equation that we have here because it's x equals as opposed to y equals. That obviously means that it's going to be a little bit weird to kind of go ahead and graph this particular curve, but we should be able to do this by, as part A suggests, creating a table of values and sketching the picture. If I'm ever unsure of what a curve looks like, I can always try to go back at least to this very basic and fundamental sort of approach of creating a table of values. There's nothing wrong with this. I even still do this from time to time. Now, if I was to take a look at something like this, I might notice that it might be easier here to start by picking values for y and then calculating what the value of x is, because it seems like that's kind of how this thing is set up to work already. So maybe I'll go ahead and I'll pick a whole bunch of different values for y like we would normally do when we pick values for x. So maybe I'll pick -2, -1, all the way up to 2. So let's see what we would end up with. If I plugged in -2, I'm going to get 4 minus 1, so I get 3. If I plugged in -1, I'm going to get 1 minus 1, that's going to be 0. If I end up with 0 plugged in, it looks like I get -1. And oh, I should notice here that if I plug in 1 or plug in 2, I'm going to get the same thing as when I plugged in -1 or -2. And so very, very quickly, I can generate a whole bunch of different points, and then I can go over here to a graph and slowly start to sketch them. All right, to a set of axes and slowly start to sketch them. So let's see, I'm going to have like -1, 0. I'm going to get 0, 1, 0, -1. So I get a point here and like a point there and a point there. And if I go out to, I don't know, say 3, I can go and get some points around maybe here. And so if I start to think about playing connect the dots with these points, then can you start to tell what kind of picture I have? Well, yeah, I actually have like a sideways parabola kind of forming here, and you can kind of see it starting to shape up. Now, this probably isn't too terribly surprising because many of you probably noticed right away, hey, if this was y equals x squared minus 1, this would have been a parabola. So the fact now that it's just y squared minus 1 just really means that this is going to be a parabola that opens in a sideways direction as opposed to up or down. So immediately, again, we can see that this is certainly not a function, right? There's no way this is a function. It doesn't pass vertical line test. Certain values of x, almost every value of x here, produces multiple different y values. As we can see here with like the x value of 0 or the x value of 3 produces different y's. But what if I was asked to go ahead and find the equation of a tangent line to this curve at the point 8, -3? Well, 8, -3 is going to be, oh gosh, I mean, I don't even really have space for it here in the picture, but I know, let's just say for the sake of argument, that's going to correspond to some point like maybe way over here, right? 8 over 3 down. And so definitely there is a tangent line here that I might want to try to find the equation of, but how am I going to do that? Well, if I'm going to leave it to you to try to think here about part B. See if you can go back to part B of the previous question and see the approach that we took and see if you can come up with an answer. So I'll ask you right now to go ahead, pause the video, see if you can work through this. And when you unpause, you'll be able to see me work through the solution. Okay, well hopefully you did take some time to go ahead and practice, at least attempt this question. Let's see kind of how I could have done this. Well, one thing to note right away is that since I'm working with the point 8, -3, I'm really only working with, I guess I could say, the bottom half of this parabola. So if I could find a formula for the bottom half of this parabola, I would be in good shape. So let's see here. I'm going to go ahead and take my equation of x equals y squared minus 1, and I'm going to try to get this to be solved for y. So notice that I could rewrite this then as y squared is equal to x plus 1, and then I could square root both sides and get plus or minus the square root of x plus 1. So I can see that the positive portion is going to correspond to the top half where y's are positive, and the negative portion is going to correspond to this red half down here. So I'll write this out by saying since we are working with the point 8 comma negative 3, we are only looking at the bottom half of the parabola. Okay, and I know that that has the function formula of y equals negative square root of x plus 1. Okay, great. So this is going to work out really, really nicely. I have this piece here that I can go ahead and actually use now, and I just need to go ahead and take its derivative. So I'll say we calculate, and let's see, I'm going to get y prime. I'm going to use my chain rule here. So I'm bringing the power of 1/2 down to the front, leave the inside the same, and leave my power subtracted by 1 up top. I need to make sure that I don't forget my negative sign that was in the front, so I'm just going to put that negative over here on my 1. Then I have to do chain rule, which is multiply by the derivative of the inside, which is really just 1 here. Okay, so if I was to simplify this all down, I would see that I get a negative 1 over a 2, and then remember I can take the square root and move it down to the bottom of that fraction. So I'm going to get x plus 1 there. Right? That's what I get because of the negative power. So here's my derivative. And so I can then state that my slope would be found by going here to my derivative and plugging in the value of 8. So it's going to be negative 1 over 2 times the square root of 8 plus 1. So that's the square root of 9, which is 3. So this is going to be negative 1 over a grand total of 6. I also can see again that I have the point of 8 comma negative 3. And so I have a point and a slope. I'm ready to set up my point slope form. So I can say the equation of the tangent is going to be given by, I'm going to have y minus negative 3, so y plus 3, is equal to a negative 1/6 times x minus 8. Now if I simplified this all the way down, and got this into a kind of a y equals form, I would have y equals negative 1/6 x. I'll notice here I end up with a positive 8/6, but I end up having to subtract 3. 3 is going to be the same as 18/6, and so I'm going to end up with negative 10 over 6 as a grand total there. So I'll get minus 10/6, although I should be able to recognize that I could reduce this by dividing top and bottom by 2, and so I'm going to end up with minus 5/3. So here would be the equation of my tangent line. And again, it should satisfy everything that it needs to. It should have a negative y-intercept, should definitely be having a negative slope. And it looks like I have that. So hopefully you were able to go ahead and actually get to a similar answer as well. So far what we've seen is that we can find tangent lines on curves that are not functions by finding hidden functions kind of resting within them, finding a formula for that hidden function, which again we kind of did right here, and then going ahead and just doing our standard approach of finding the equation of a tangent line. But let's take a look at one final question before we end this video. What if I asked us to do the exact same sort of process here on this question? Why would finding the equation of a tangent line on this graph, which you'll actually notice is the exact same graph that we were working with up here at the beginning. So this is kind of loop-de-loop graph. But why would that be difficult to do at the point 3 comma 3? I mean, couldn't we just take the same exact approach, right? So like maybe there's, on that particular picture, which looks something like this, maybe in here there's, go ahead and draw the axes kind of over this, but the picture looked something like this. So maybe in this particular picture, there's some hidden functions within here, and 3 comma 3 actually ends up being the point kind of right up here. So maybe if I could find a function that would work, then I could just take or find a function that contains this point, I could just go ahead and take the derivative and do all the same stuff that we did in the last two examples. So maybe what I would need to do is start by just doing the same thing that we did up here. I would take the equation and maybe solve it to say y equals, and then maybe then I can figure out what part corresponds to a curve going through this point. Okay, so maybe we can try to solve this for y. Any ideas? Take a look at it for a second. X cubed plus y squared equals 6xy. I'm going to even ask the question, can we solve for y? This is actually going to be difficult. This is really difficult. How in the world are we going to solve to have this say y equals? Well, I'll answer the question here not by saying no, but instead by saying not easily. There is actually a way that we could solve this for y, and that would be using something called the cubic formula. Now, if you've never heard of the cubic formula, it's kind of like the quadratic formula. A quadratic formula was used to arbitrarily solve any quadratic equation, and the cubic formula is used to solve any cubic equation. And so it's possible that I could rewrite my equation here to look like y cubed minus 6xy plus in x cubed equals a 0. So I can see I have y cubes, no y squareds, y's to the first, and if I imagine x is kind of just like a number, I imagine this is like a cubic function set equal to 0. So you could use a cubic formula here, but if you're interested, go ahead and try to Google the cubic formula. It looks horrible. Nobody wants to use the cubic formula. And so my answer here is certainly this is not going to be easy to do. Not going to be easy. And there may even exist other sorts of curves where it is maybe even impossible to solve for the variable that I want and then try to figure out what a formula would be for like a little portion of our function or a little portion of our curve that maybe goes through our particular point of interest. So our real question, our real dilemma at this point is what in the world are we actually going to do now that we actually are witnessing equations that are not so easy to solve for y and just identify, oh, I'm working with this side, and so I can easily just take a formula for that side and repeat our standard process. What are we to do? Well, we'll talk more about that in the next video.